Yes, good morning. My name is Pantea and hello from sunny Sydney. Yes, today I'd like to present you with a presentation that was actually done by my supervisor, Peter Kim, from the University of Sydney. He did this project alongside Peter Lee from the City of Hope and Dorian Levy from the University of Maryland. Now, the aim of this project was to take a well-established ABM model and produce an equivalent PDE system. And there are advantages to this, which I'll describe in a few slides' time. So just a little bit about the biology behind this model. We have these hematopoietic stem cells. I can't believe I just said that word, hematopoietic. These stem cells actually derived in our bone marrow. And these stem cells actually have this nice feature where they then differentiate into these progenitor cells, and from there they can differentiate into these different types of specialized blood cells. So before they actually differentiate right down here, these stem cells can actually transition into the progenitor phase and then kind of transition back into a stem cell phase. And the ABM actually models this process, but we can sort of, I think what we need to try and think about here for this model is that this process can happen not just sort of between these two types, but it can happen on a bit of a spectrum. So the differentiation can happen on a bit of a spectrum until it reaches down here where they become these differentiated blood cells. So that's the idea behind the model, and we're not really going to go into the biology of this. This is just to describe what's happening with the ABM. So the original ABM was designed by Rhoda and it was published in Nature magazine in 2006. And this model has two different types of agents. We have these quiescent stem cells and proliferating stem cells. Both stem cells can have these state variables for the differentiation levels between 0 and 1. So a cell that is has a differentiation level of 0 is a full stem cell, and if it reaches all the way to 1, then it's a fully differentiated cell. The proliferating stem cells, they also have this cell clock. So this cell clock represents the natural cell cycle for the proliferating cells. So from when their cell clock reaches C1, they actually divide, and then from C1 back to 0 is when they're kind of in a G1 phase. So these quiescent cells and proliferating cells, they can transition between each other, but when these A cells want to transition to proliferating, they need to enter from this entry point 0, and the cells that are proliferating and they want to sort of return back, they need to wait till they're in the G1 phase. Okay, so I think that's it for that slide. Now, let's talk a little bit more about this algorithm. We've got these quiescent cells. They can transition with probability omega into a proliferating cell, and the proliferating cells, they can transition back to an A cell with probability of alpha. So these probabilities are dependent on the differentiation level X and the total populations, omega and alpha. These represent total populations as well. Sorry, really confusing. So the proliferating cells, they actually divide at when the clock reaches C1. The other feature that is really important about this is that if a cell is still in the A population at the next time step, it loses, its differentiation level decreases and decreases by rho R. If a cell is still in a proliferating population at the next time step, it gains a differentiation level, and that's done in increments of rho D. And the time step for the model is every hour, and the cell clock, yes, that increases every hour as well. Okay, the transition probabilities, just a little bit more about these. So as you can see, so these are the definitions for the transition probabilities. As I said, the transitions depend on the differentiation level, but also on the total populations. So if the population of A, for example, is quite large, the probability of transitioning to this population becomes lower. The way the author of the paper describes the transition probabilities is that if an A cell remains, I guess, for a long time in this population, the longer a cell remains in this population, the less likely it is to transfer back to the other population. population. That is the description given by the author, just to help visualize the idea. Okay, so let's talk about some of the attributes, good and bad, with this agent-based model. So like other agent-based model, it accounts for individual diversity and probabilistic transitions. But on the downside, this model is very computationally demanding. The authors actually simulated approximately 100,000 cells, and this is only a tenth of the realistic value. And each of these simulations took approximately 7 hours. Now, they need to be repeated 20 to 50 times, so that means about 1 to 2 weeks of computational times. So really, really computationally costly. So this is a nice motivation. And when you're actually, I guess, working with really large numbers like this might be a nice motivation to consider a PDE system. So the advantages. So we can work obviously in this standard mathematical framework that we all are familiar with. It's computationally simpler and easier to vary parameters continuously. I mean, we may want to do certain analysis like a parameter sensitivity analysis. So this becomes a little bit simpler with a PDE system. So I'm going to show you, I'm not going to show you because I just went back up. I would like to show you sort of a heuristic construction of the PDE for this system. So what we're going to look at here is, let's first consider the population A. So let A of xt denote the population of the density of the A cells, the quiescent cells, with differentiation level x at time t. If we consider this differentiation scale, we can think about this rho r, this previous incremental reduction in x as more of a flow. Hence, in our A population, we have this advection term to the left. We can then think about these probabilistic transitions, cells moving out and coming in. Now, in the original ABM model, the model was calculated at every hourly time step. So if we are to calculate our PDE per hour, we can sort of change these probabilities into rates. And that's exactly what we do in this model. We now consider these as rates. So here we have the rate out and the rate coming in. Now these limits here are for the rate coming in is because, as you remember, these cells can only transition from the amiga population during their G1 phase. Okay, so then this brings us to this A star compartment, and why is this needed? Well, when we run this numerically, you have this kind of large flow coming towards this boundary of x0. And when this happens, we end up with quite a stiff PDE because it tends to blow up at this corner, at this boundary. So instead of this, what we can do is we can take these cells and put them into this compartment of A star. And then that means for the A star population, we now have this nice ODE with a rate of cells coming in and a rate of cells leaving A star. And these cells actually move into omega star, which I'll show you in the next slide. We also need to consider the boundary conditions. So at the boundary on this end, we have no cells coming in, or we have no cells. And that's because these cells actually differentiate and completely leave the system from the other side. Okay, let's take a quick look at the omega population. So sorry, this is quite an intense and dense slide, but I'll break it down. So on this axis, on the y-axis, we have this cell cycle. It goes from 0. At C1, the cells divide, and at C2 is, I guess, between C1 and C2 is the G1 phase. Cells that reach C2, they come back in through this boundary. On the x-axis, we have the differentiation levels from 0 to 1. This time, our flow is running to the right. So here we have the flow to the right. This is the change in our counter, in our cell clock counter. And we have the cells that are leaving, and they need to be, and the cells that are leaving this population, they leave from this G1 state. In the second set of PDEs that are developed, we have the cells that are coming in from A star. Now these cells, they just travel along these characteristic lines. Yes, they just move along these characteristic lines, and if cells are going to be leaving this population, they again leave from the omega star. We do again need to, when we're developing these PDEs, obviously we need to be thinking about boundaries. So we have this boundary at x equals to 0, at c equals to 0, and at this boundary we have the cells that are coming back in from C2, but also the new cells that are entering from the A population. They enter through this boundary here. This here is what's happening at the boundary of 0 for the omega star cells, and this is just a scaling because of the A population. Okay, so I don't, let's not go into too much detail, but here's the full PDE system. As I said, this is done in that more heuristic way, and we have a few other boundaries that we need to consider. Now, obviously, this could be done in a different way, but for this model, we took the cells that are doubling at this point, and we think of this as a boundary, and this is where we get a doubling of cells. So let's just look at some of the results from the comparison between the ABM and the PDE. As I said, the biology here isn't important, but what I'm trying to show you is the similarity between the two results. So we can see that the PDE, we have the PDE and the ABM. The ABM is in the blue and the red, and the PDE is actually a nice average approximation for the ABM. This is the steady state profile, so this is number of cells and the cell differentiation levels. For the ABM, it looks this way because the differentiation levels have been grouped into wells, so that's why we get this sort of this kind of shape. On the bottom, we have the time evolution for different advection rates, and again we can see that our PDE is actually a really nice approximation for the agent base. Okay, so as I just said, the PDE is actually a good approximation for the ABM, and we need to obviously stress here that this is for large populations. It probably wouldn't do as good a job for a much smaller population. But also it's computationally a lot faster. We have these 5-minute simulations as opposed to 7 hours for each simulation with the ABM. And yes, it's definitely more amenable to analysis, so easier to identify important parameters and much easier and quicker to make these adjustments. Okay, so that was taking the model in a heuristic way, so taking the agent base to a PDE, but this is not always possible, and it's not always easy to do that. And it's not, if we want to also maybe put in some rigor in there, what we can do is perhaps have this intermediate step of having a set of difference equations. So I want to quickly show you how we would develop the difference equations for this particular model. Oh, and I am again going way too far back. Here we go. Okay, so the first thing we need to do is we're going to, I will use the A population as the example. We're going to take this differentiation scale and we're going to discretize this. And then we're going to think of a cell at position xj at time tn. And we can then write a set of update rules, just like an ABM, for the next time steps, so that the population from xj plus 1, they're going to move down one level. We're going to have cells that are going to be leaving, cells that are going to be entering, and we also need to be thinking about what's happening at our boundaries. When we do this, we end up with a set of difference equations. So we can write these difference equations for the population along x, and we can also do this at the boundary of x equals 0 and the boundary of x equals to 1. We can take these equations and rearrange them, and hopefully if we arrange them in a nice manner, we can then take the limits of delta x and delta t to 0. And when we do this, we can recover our original PDE system as before. And again, this is for the A population, and we can do this again for the Omega and the Omega star population. And we come back to the same PDE system that we derived previously. So, as I said, we can do all kinds of analysis for the PDE system. This was analysis that was done on this model. And really, just in conclusion, what we can do is we can translate this ABM model either heuristically, or we can take it through this set of difference equations, and hopefully these difference equations are going to be some kind of a numerical scheme for a PDE system. But this is something to consider if you're finding that your ABM is sort of too costly, or it's taking a long time, or perhaps your populations are sort of quite large, and perhaps the law of average number is going to apply to your model. Yes, thank you so much for your time this morning.
Thank you very much, Pantea. Very nice work. Also, thank you so much for joining at 6 a.m. Australia time. We all very much appreciated your presentation.
My pleasure.
It was a great way to close off today, where we talked about the agent-based modeling and also the computational work with PhysiCell, now to see it taken to a PDE. Just before we say our final kind of goodbyes today, there were a question or two in the chat that I just wanted to pose one of them to you so it could be asked, and then
yes, I'll do my best. Yes. Yes.
So someone has asked if there is an advantage from going to agent-based models to difference equations, to PDEs versus experimental data. So it seems like replacing an ABM would be an opportunity to align with more real-world data. So could you maybe comment on your thoughts about ABMs versus PDEs and taking them between the two?
Oh, okay. So the person wants to know, is saying that perhaps an ABM is more in line with the real world data. Is that, sorry, was that?
Yeah, I guess that's the question from your kind of experience with PDEs and ABMs and.
Okay, so yes, this can be true. Yes, this can very well be true. But at times when we are dealing with really large sets of like we said, large sets of cells or large populations, these can at times average out. So it really depends on what the aim of your model is. Are you trying to look at how what's happening between individual cells and their interactions, or are you looking at a larger picture? If you're looking at a larger picture, sometimes, as I said, these things can average out and you can get the overall behavior. So it really comes down to as we said, the computational cost versus the gain. So yes, an ABM can be great, but what are we trying to see? I've used an ABM before where we can actually look at how different types of cells can spread and what sort of a spread you get within tissue, perhaps. That was really important to do that in an agent-based type of model. But then there's times where I've used an agent-based and then become frustrated and you know, because it would take so long to run it, and moved into a PDE system, and that's been able to do a job just as well. So it really depends on your overall goal.
Great. Well, Madeline, and just thank you for your answer. So great job. So I guess if there are any more questions for Pantea, I think she'd be very happy to answer them via email at any chance.